January 1940. The Midwestern winter pressed against factory windows, frosting the glass with delicate patterns that masked the industrious chaos within. Outside, snow lay heavy on rooftops, muffling the occasional rumble of a delivery truck or the distant clang of a train. Inside, the factory floor pulsed with restrained energy, machines standing in silence, their belts slack and cold steel gleaming under the pale light of overhead lamps. It was a space designed for movement, for speed, for productivity, but now it was frozen by a problem almost invisible to the untrained eye. A single component, so small it could rest in a man's palm, had become a choke point for the entire industrial system. A ball bearing. Smooth, hardened, perfectly spherical, yet entirely absent from the line. It was a component that, when present, ensured the flawless rotation of shafts, the steady operation of engines, the reliable function of gearboxes in tanks, aircraft, and naval vessels. Without it, machinery halted. Production slowed. Timelines stretched. In January 1940, America was beginning to feel the consequences of this missing precision. Engineers crouched over drafting tables, pencils moving across blueprints spread flat like battle maps. Each line, each measurement was exact, dimensions noted down to thousandths of an inch, calculations annotated with grease and chalk, tolerances marked in decimals. Yet despite this meticulous planning, the factory could not move forward. The machines, designed to obey the engineer's precise intent, waited for the one part that was missing. In the corner of the plant, a machinist lifted a freshly forged crankshaft from a lathe, its surface polished to a sheen. He ran his hand along it, feeling the rhythm, the weight, the balance. It was perfect in every respect, but it could not turn, could not fulfill its purpose, without the bearing designed to fit snugly within its assembly. The delay was invisible to the outside world, but to those inside, it was catastrophic. Across the Atlantic, Europe had already plunged into war. German factories hummed day and night, not with the casual pace of civilian industry, but with disciplined, machine-like precision. Every component was standardized, every production line optimized for wartime conditions. Bearings flowed in a predictable rhythm from foundry to assembly hall. Engineers adjusted, recalibrated, and perfected with a confidence born from years of preparation. In Japan, similar attention to precision and import-dependent specialization created a mirrored system, smaller, more fragile, yet equally methodical. Axis intelligence had its eye on America, albeit with limited understanding. Reports noted the scale of American industry, the sheer number of factories, the abundance of steel, the availability of labor, but underestimated one crucial element: the speed at which American engineers could adapt. Europe's assumption was simple. America, unaccustomed to war, untested in large-scale military production, would falter. Bottlenecks, like the missing ball bearing, would multiply, delaying readiness by months, possibly years. The belief was that industrial capacity alone could not compensate for a lack of specialization. Inside the U.S., however, the reality was subtler. Factories were massive, yes, but scattered. Small shops, medium-sized plants, and large-scale production halls each contributed to the industrial landscape. This decentralization, while frustrating in peacetime logistics, contained a latent potential that would soon become apparent. The missing bearing, the halted lathe, the delayed shipment, these were not signals of inevitable failure, but catalysts for innovation. Engineers began to consider alternatives. They measured, adjusted, and experimented. They asked questions that no one had asked before. Could a different type of bearing do the same job? Could tolerances be relaxed slightly without catastrophic failure? Could machines be redesigned to accommodate what was available, rather than waiting for what was not? In Washington, officials tracked these developments through memoranda and production reports. They noted delays, but the scale of the problem was often hidden behind abstract numbers. Thousands of engines awaiting components, hundreds of tanks with incomplete drivetrains, naval turbines missing critical pieces. The significance of these small components, the ball bearings, the rollers, the precision-machined parts, was almost invisible to those accustomed to thinking in millions of dollars or thousands of tons of steel. Yet in practical terms, a missing bearing could halt an entire shipyard, immobilize a battalion of tanks, or ground a squadron of aircraft. Engineers, machinists, and supervisors felt the weight of responsibility. Their work was quiet, unseen, yet essential. They understood that war would not wait. Battles would not pause for a shortage of components. Europe's front lines were moving. Poland had fallen. France was under siege. Germany's mechanized divisions cut through defenses with staggering speed. And the United States, still neutral, was beginning to see the limits of its industrial peacetime assumptions. In the corner of one assembly hall, a foreman examined a stack of tapered rollers, newly forged as a potential substitute for the unavailable ball bearings. He rotated one in his hand, testing its fit against a gearbox. It was not ideal, but it was functional. Nearby, a young engineer adjusted the blueprint of an aircraft engine, changing the spacing of its shafts to accommodate a different bearing. These were small, deliberate acts of improvisation, carried out under the calm pressure of necessity. Outside the plant, the winter sun cast long shadows across snow-dusted streets. Delivery trucks waited to transport materials that might or might not arrive in time. Trains carried steel and machine tools across the Midwest. Ports prepared for shipments that could supply allied nations or sustain America's own nascent mobilization. The entire ecosystem depended on coordination, innovation, and adaptation, all sparked by the absence of a single, seemingly insignificant component. This quiet, urgent ballet, engineers solving problems minute by minute, machinists adjusting to unforeseen challenges, factories testing substitutions and redesigns, would lay the foundation for America's industrial response to war. By the end of 1940, it would be clear that the United States had discovered a new weapon, not a gun or a plane, but the ability to adapt, improvise, and overcome the constraints of raw material and pre-war assumptions. And so, on that frozen January morning, with machines standing silent yet poised, with snow pressing against steel windows, and with a single missing bearing halting production, the United States began to reinvent what it meant to manufacture for war. Small, invisible, unglamorous, the ball bearing became a symbol, a test, a challenge that would reveal not weakness, but latent strength. It was a moment that few would witness, fewer would record, and almost no one would dramatize, but it would ripple through the coming years, shaping the machinery, the logistics, and ultimately the outcome of the Second World War. From this frozen factory floor, the stage was set for a transformation that would make American industry a decisive force long before the first soldiers crossed the ocean in force. By the closing months of 1939, the world had entered a precarious balance that only a few understood in full. Europe was at war, though in a state that many called the phony war, a period of tense stillness after Germany's invasion of Poland, before the Blitzkrieg swept across Western Europe. Yet beneath this apparent pause, industrial systems were already operating at a tempo that would define the outcome of conflict for years to come. Factories in Berlin, Munich, and Essen were running day and night, churning out components with an efficiency born from years of preparation. Every bolt, shaft, and bearing was accounted for. Every machine tool had a purpose. Every line followed a rhythm that was deliberate, predictable, and remarkably precise. This was not happenstance. It was the product of deliberate planning, rigorous standardization, and centralized oversight that the Reich had cultivated since the early 1930s. Germany's focus on industrial precision created a competitive advantage few Americans at the time fully appreciated. Bearings, in particular, were considered foundational. They were small, often overlooked, but absolutely critical. Tightly manufactured ball bearings ensured that engines could rotate at unprecedented speeds without seizing. They allowed tanks' turrets to traverse smoothly and artillery recoil systems to function consistently. In essence, the German war machine, its tanks, planes, and ships, depended on these tiny spheres of hardened steel. SKF, the Swedish-origin bearing manufacturer with subsidiaries in Germany, became a linchpin in this network. Plants specialized not only in producing standard sizes, but in creating high-performance bearings for engines, gearboxes, and turbines. Each facility knew its output schedule to the hour. Quality control was strict, unyielding, and largely centralized. Replacement parts, spares, and contingency plans were built into the system long before the first shot of war was fired. Japan, meanwhile, was industrially capable but heavily dependent on imports and pre-war stockpiling for specialized components. While their own domestic industry could supply certain quantities for ultra-precision equipment, particularly for naval engines and aircraft, the Japanese relied on imports from Germany or neutral European nations. This dependency created vulnerabilities. Supply disruptions, whether from war, blockade, or transportation failure, had the potential to bottleneck the entire Japanese war effort. Japanese industrial planners were acutely aware of this risk and sought to mitigate it through stockpiling, but the methods were expensive, slow, and inflexible. Across the Atlantic, the United States presented a stark contrast. American industrial capacity was immense in scale, but largely optimized for civilian output. Factories were designed to produce automobiles, radios, household appliances, and farm equipment. Standardization existed, but it was oriented toward volume and affordability rather than extreme precision. Bearings were produced in large numbers, but they often did not meet the tight tolerances required for the next generation of combat aircraft or naval turbines. Specialized machine tools capable of producing ultra-high precision components were scarce, often imported, and concentrated in a handful of facilities. Yet the U.S. had advantages that would become increasingly apparent. Labor was abundant and increasingly skilled. Raw materials, steel, aluminum, copper, and nickel, were available in quantities unmatched by most nations. Industrial culture favored innovation and improvisation. Where European systems relied on strict standardization and centralized control, American firms were decentralized, diverse, and flexible. They could, under pressure, reorganize production faster than any rigid, centralized system might allow. At the time, few realized this potential. The nation was still in a state of official neutrality, politically and psychologically unprepared for large-scale war mobilization. The War Department and Navy Department monitored these realities cautiously. Reports flowed in about production shortfalls, material bottlenecks, and the limitations of domestic manufacturing. Aviation engineers expressed concern that engines could not be built fast enough for a modern air force. Naval officers noted that turbine components were not being produced at the rate required for fleet expansion. These reports were treated as advisories, not emergencies. In many ways, the American system was still governed by the peacetime mindset: incremental improvements, conservative investment, and avoidance of risk. However, in workshops and small engineering offices, a different reality was unfolding. Engineers recognized that traditional manufacturing methods could not meet wartime demands. Critical components, like high-precision bearings, were scarce. Each day of delay threatened not just production schedules, but the credibility of America's eventual war effort. Some engineers proposed substitutions: tapered rollers instead of ball bearings, modified shafts to accept different tolerances, and experimental alloys to reduce wear. Others began to rethink assembly lines, suggesting decentralized production to bypass bottlenecks in large plants. Axis intelligence, observing these developments from afar, interpreted the situation differently. Reports emphasized the United States' lack of central control, the fragmentation of industrial facilities, and the perceived inefficiency of its decentralized system. German analysts believed that America, despite its size, could not retool fast enough to influence the war in Europe before Germany achieved decisive victories. Japanese planners drew similar conclusions, assuming that U.S. production delays would prevent timely intervention in the Pacific. In both cases, the assumption was that raw industrial capacity could not substitute for specialized expertise. America, they concluded, was powerful but slow. Meanwhile, back in the United States, subtle but decisive changes were beginning. Firms previously confined to civilian products began experimenting with military adaptations. Bearings designed for automotive use were tested under more extreme conditions. Factories examined their processes, identifying points where precision could be maintained without absolute adherence to pre-war tolerances. Engineers held informal consultations across companies, sharing methods for accelerating production while avoiding catastrophic failure. This collaboration, unusual in peacetime industry, was a precursor to what would become a nationwide mobilization strategy. By the spring of 1940, the contrast between expectation and reality was becoming clear. European observers anticipated American delays measured in years. In fact, American engineers were discovering that, with adaptation, months could be sufficient. Small workshops could produce high-quality components at scale if processes were modified and tolerances adjusted. Statistical quality control, still novel in many plants, began to be applied rigorously, allowing factories to maintain performance even when parts deviated slightly from original specifications. It was still early. Factories did not hum at full speed. Bearings were still missing. Production lines stalled. Yet a transformation had begun. Engineers and managers were learning to see obstacles not as insurmountable, but as challenges to be overcome with ingenuity, collaboration, and relentless measurement. The same qualities that had made American industry efficient in peace, flexibility, decentralization, innovation, were quietly being adapted for war. And as Europe prepared for the blitzkrieg against France, Belgium, and the Low Countries, the United States stood on the edge of an industrial awakening. The missing bearings, the halted engines, the delayed shipments, they were harbingers, not of failure, but of the ingenuity that would soon allow America to produce war machines at a pace the world had never seen. The Axis assumption that precision could not be improvised was about to be tested, and quietly, methodically, American industry was preparing to prove them wrong. This growing tension between expectation and adaptation set the stage for the decisive transformation of American manufacturing and, ultimately, the United States' emergence as an industrial powerhouse capable of shaping the outcome of the war. Across the industrial heartland, the impact of missing components was felt in very concrete ways. In Detroit, the city known as the Arsenal of Democracy, even before FDR's speeches, automotive plants had been pressed into preliminary aircraft engine production. Workers accustomed to stamping chassis and assembling carburetors now confronted engine blocks designed for extreme stresses and precision tolerances that far exceeded anything encountered in civilian work. Blueprints arrived with annotations in fine pencil, diameter measurements in thousandths of an inch, bearing placements exact to microns. Yet for each component produced, engineers discovered gaps, tiny imperfections that, if multiplied across hundreds of engines, could ground squadrons of aircraft in weeks. In the Midwest steel towns of Ohio and Indiana, rolling mills churned day and night, producing alloy steel that could withstand high temperatures and extreme mechanical loads. Engineers experimented with new heat treatments and metallurgical processes, seeking ways to reduce the risk of early wear in bearings and gears. At first, many tests failed. Shafts cracked, gears warped, and test rigs ground to a halt. Each failure, however, became a learning moment. Notes were meticulously taken, adjustments calculated, and new prototypes produced with faster turnaround. The urgency was palpable. Each delay was not just a production problem. It was a potential strategic failure. The Navy faced a parallel challenge. Shipyards in New York, Philadelphia, and along the Gulf Coast expanded rapidly, constructing destroyers, cruisers, and submarines. Turbines and reduction gears depended on bearings capable of withstanding weeks of continuous operation at sea. Delays in delivery forced engineers to consider redesigns, alternative suppliers, and substitute materials. Some shops adapted rolling contact bearings originally intended for railroad locomotives to marine applications, a stopgap that required careful testing but maintained production schedules. These improvisations, though minor on paper, were monumental in practice, allowing shipbuilding to continue despite material shortages. Washington's response was measured but increasingly urgent. Military procurement agencies began cataloging critical component shortages, tracking suppliers, and prioritizing deliveries. Memoranda circulated noting that high-performance bearings were the single most significant constraint across aircraft, armor, and naval programs. While public speeches continued to emphasize peace and neutrality, internal planning recognized that war could no longer be postponed. The War Department encouraged collaboration between civilian engineers and military planners, fostering a network that bypassed traditional bureaucratic obstacles. Meanwhile, Axis intelligence misread the unfolding scene. Reports highlighted the fragmented nature of U.S. manufacturing, the lack of centralized planning, and the apparent dependence on imported tooling. Germany and Japan both assumed that even if America entered the war, Industrial adaptation would take years, leaving Europe and the Pacific in Axis hands for the foreseeable future. The consensus among German analysts was that the U.S. lacked both the technical specialization and the wartime experience to produce high-quality engines and armaments at the pace modern combat demanded. In Tokyo, planners shared similar assumptions, calculating that the industrial output of American factories, while large, would arrive too late to influence early campaigns in the Pacific. Yet behind these assumptions, American factories were already beginning to rewrite the rules. Engineers implemented statistical process controls, using sampling and measurement to detect variations in parts before they could halt production. Tolerance standards were reconsidered. Could slightly larger or smaller bearings work if aligned differently? Could shaft housings be modified to accommodate variations in production? Small workshops that had never produced military-grade parts were brought into the network, provided with drawings and guidance, and allowed to innovate methods to meet the specifications. Cross-company collaboration, unusual in peacetime industry, became routine. This distributed, adaptive approach foreshadowed the full mobilization of the U.S. industrial machine in the coming years. By mid-1940, the United States faced a paradox. The country appeared unprepared in theory, yet capable in practice. Bearings were still missing. Production lines still paused. Yet the pace of problem-solving accelerated. Engineers and machinists learned to see shortages not as insurmountable obstacles, but as triggers for innovation. They tested, measured, adjusted, and shared results with unprecedented speed. Where Axis planners assumed delay, American ingenuity began to create momentum. This momentum was subtle. It did not announce itself in headlines or speeches. No soldier witnessed it on the battlefield. Yet its effects would be decisive. By the time France fell in June 1940, the United States had begun the quiet transformation that would underpin its industrial dominance in the years to come. Factories that once stopped for a missing ball bearing were beginning to produce alternative solutions, redesign critical components, and maintain the pace of production under conditions that would have seemed impossible in 1939. The bearing shortage, invisible to most observers, had become a catalyst. It forced engineers, managers, and policymakers to confront the limits of existing processes, to collaborate across sectors, and to innovate under pressure. By challenging the assumptions of American industry, it revealed a latent capability that would soon prove central to victory: adaptability at scale. As Europe burned and Axis confidence swelled, the seeds of America's industrial revolution were quietly taking root. A revolution measured not in tanks or planes, but in the ingenuity of engineers who refused to let a small piece of metal dictate the fate of nations. As 1940 progressed, the challenges in American industrial production became increasingly tangible across multiple military programs. Aircraft manufacturing was among the first to reveal the strain. The Army Air Corps, anticipating future engagement, had ordered the latest generation of combat aircraft, sleek monoplanes capable of higher speeds, greater altitudes, and heavier payloads than their 1930s predecessors. These designs demanded engines with tighter tolerances and components that could withstand sustained operational stress. Bearings that had sufficed for civilian airplanes or pre-war trainers now proved inadequate. Crankshafts and reduction gears experienced accelerated wear. Test flights were delayed, not because of human error or insufficient planning, but because the minute parts at the heart of each engine were either unavailable or inconsistent in quality. Tank production faced a parallel problem. The new M2 and M3 series required drivetrains capable of transferring significant torque under combat conditions. Gearboxes, turrets, and suspension systems all relied on bearings that could tolerate high loads and constant movement. Factories producing these components struggled to meet specifications using the tools and materials available, and even small deviations risked mechanical failure in the field. Engineers responded by redesigning housings and tolerances, experimenting with alternative materials, and repurposing bearings from civilian applications, a calculated gamble that, if executed carefully, allowed production to continue. Naval programs highlighted another layer of complexity. Battleships and destroyers required turbines that could operate continuously for weeks at sea without failure. Bearings within these turbines were critical. A single malfunction could compromise propulsion, navigation, and combat effectiveness. Shipyards along the East Coast, Gulf Coast, and Great Lakes had to coordinate with steel mills, forging plants, and machine shops across the country. Every shipment, every component, had to arrive on time. Delays in small parts like bearings threatened entire construction schedules. Engineers and procurement officers devised new quality assurance protocols and contingency plans to prevent minor shortages from halting major programs. Tapered roller bearings, previously reserved for heavy industrial machinery, were adapted to marine turbines, with design modifications that allowed them to function reliably under high load. Government agencies began taking a more active role. The Army and Navy established interdepartmental committees to monitor shortages, coordinate production, and prioritize critical programs. Memoranda circulated outlining which plants were capable of producing precision components, which suppliers could be brought online quickly, and where alternative designs could substitute for scarce parts. The goal was clear: prevent a single missing component from crippling a production line. Yet these measures were carefully balanced. The United States remained officially neutral, and public perception could not be alarmed. Most of these changes unfolded quietly, within the industrial and military bureaucracy, even as Axis observers attempted to interpret the nation's readiness from afar. In Berlin, intelligence officers continued to monitor American industrial reports with a mix of curiosity and skepticism. They saw fragmented factories, inconsistent output, and a reliance on imported machine tools as signs of weakness. German military planners believed the United States would take years to adapt to wartime production demands, underestimating the speed with which engineers could experiment, redesign, and implement new methods. In Tokyo, similar assumptions held sway. Japanese analysts acknowledged the scale of American industrial capacity, but doubted that decentralized, civilian-oriented factories could pivot quickly enough to affect early campaigns in the Pacific. Yet the United States was already proving this assumption wrong. Engineers and small machine shops were producing critical components using innovative techniques. Larger plants adapted their assembly lines to incorporate new tolerances and alternative materials. Statistical quality control methods, though still new, were applied systematically to identify errors before they could cascade into failures. Cross-company collaboration accelerated problem-solving. Substitutions that would have been considered unacceptable in peacetime were now rigorously tested and deployed. In effect, American industry was improvising at scale, learning in real time how to overcome bottlenecks without halting overall production. One illustrative example was the production of high-performance aircraft engines. Factories in Dayton, Ohio, and Indianapolis, Indiana, had been struggling with delays caused by missing ball bearings. Engineers experimented with modified tapered rollers and redesigned housings, allowing engines to operate reliably despite small deviations from original specifications. Test pilots reported that these engines performed under sustained flight, confirming that the substitution was viable. Within months, this approach became a model for other critical components. Adapt the design to the factory, rather than waiting for the factory to match the design. By the summer of 1940, the impact of these changes was beginning to be measured. Production schedules stabilized. Engine deliveries increased. Tanks and ships could be assembled on time. More importantly, the process of solving these bottlenecks created a culture of resilience and innovation. Factories were no longer passive machines waiting for parts. They were active problem-solving ecosystems capable of rapid adaptation. The tension between Axis expectations and American industrial reality set the stage for a decisive transformation. While Berlin and Tokyo assumed delays, American engineers were quietly redefining the limits of wartime manufacturing, demonstrating that even the smallest missing component could be overcome with ingenuity, collaboration, and determination. Beyond individual factories, the transformation was systemic. By mid-1940, coordination between industries had accelerated. The Army, Navy, and civilian manufacturers began sharing data on production capacities, component availability, and anticipated bottlenecks. Meetings between engineers, procurement officers, and plant managers became routine, fostering collaboration that would have been unthinkable in peacetime. Paper trails of memos, charts, and annotated blueprints crisscrossed the Midwest, Northeast, and Southern industrial hubs. Each document captured a fragment of a larger problem, and together they began to outline a network capable of producing complex war material under unprecedented constraints. Rail networks became arteries of adaptation. Raw materials moved from steel mills in Pittsburgh and Youngstown to engine assembly plants in Dayton and Detroit. Precision components traveled from small machine shops in Ohio and Indiana to naval yards along the Atlantic coast. Timing was critical. Delays of even a few days threatened to cascade across multiple production lines. Engineers developed detailed scheduling systems to monitor shipments, track progress, and anticipate shortages. In some cases, alternative routing allowed shipments to bypass bottleneck depots, demonstrating an early form of logistical flexibility that would characterize the American war effort in years to come. Government policies supported these adaptations. Though the U.S. remained officially neutral, federal agencies quietly encouraged manufacturers to prioritize projects with potential wartime applications. The National Advisory Committee for Aeronautics, NACA, facilitated the testing and redesign of aircraft engines. The Bureau of Ships coordinated with private yards to ensure that turbine components and critical bearings could be produced on schedule. Early planning for what would become the War Production Board was already underway, providing guidance and authority to align private industry with strategic military needs. These initiatives blurred the lines between civilian and military production, transforming the industrial landscape without publicly signaling the shift. Meanwhile, Axis observers struggled to interpret the unfolding changes. Reports from German intelligence noted apparent improvements in American industrial efficiency, but the decentralized, adaptive nature of these developments was largely invisible from afar. Analysts assumed that the pace of U.S. adaptation would remain slower than Europe's highly regimented systems. Japanese reports mirrored this assumption, underestimating how quickly small, flexible workshops could integrate into a larger national effort. Both Axis powers failed to recognize that adaptability, not perfection, would become the defining feature of American wartime production. The consequences of these developments began to ripple beyond factory walls. Military planners observed that components were arriving more consistently, engines performed reliably under test, and assembly lines maintained momentum despite earlier shortages. This newfound reliability allowed commanders to plan operations with greater confidence. Training schedules, deployment timelines, and equipment allocations were no longer dictated by the risk of mechanical failure. Engineers and factory managers, previously constrained by traditional notions of perfection, now operated with a pragmatic philosophy. Function under stress was more valuable than flawless but delayed components. Strategically, this period set a precedent that would shape the coming years. When France fell to Germany in June 1940, and Britain prepared for the Battle of Britain, U.S. industrial adaptation had already proven that perceived weaknesses could be overcome. The missing bearings, the delayed engines, the halted production lines, all had become tests of ingenuity and coordination. Each obstacle surmounted built confidence in the system itself, laying the foundation for the massive wartime mobilization that would follow Pearl Harbor. By the end of 1940, a subtle but decisive transformation had taken place. American industry had learned to anticipate shortages, adapt designs, and integrate decentralized production into a coherent, resilient system. Factories that had once paused for missing bearings were now capable of redesigning assemblies on the fly, testing substitutes, and maintaining output under pressure. Engineers, machinists, and military planners had collectively created a network of innovation and resilience, invisible to most observers, yet critical to the future Allied war effort. As the world edged closer to global conflict, the United States quietly prepared not just to enter the war, but to redefine how war could be fought, through industry, ingenuity, and adaptability. The missing bearing of January 1940 was no longer a limitation. It had become a catalyst for an industrial revolution that would underpin victory. In the winter of 1940, the true battle was not on distant battlefields but in workshops, offices, and factory floors across the United States. Engineers, many of whom had never imagined themselves part of a war effort, suddenly found their expertise under immense scrutiny. Each missing bearing, each delayed component, became a personal challenge, an obstacle to be solved, not lamented. They worked in dimly lit rooms, blueprints spread across drafting tables, pencils tracing tolerances in thousandths of an inch. Calculations were double-checked, materials tested, and prototypes built with meticulous care. The pressure was relentless. Schedules were tight, resources limited, and the stakes immeasurable. One faulty calculation could delay an aircraft assembly by days, grounding squadrons that might soon be needed overseas. Engineers collaborated in small teams, sharing knowledge across departments, sometimes across states. Solutions were rarely perfect at first. Bearings were substituted, housings modified, shafts recalibrated. Each success brought confidence. Each failure taught a lesson. The sense of urgency was palpable, yet the work was quiet, almost invisible. Heroes in lab coats and overalls rather than uniforms. Yet these individuals were more than technicians. They embodied resilience and ingenuity, turning constraints into catalysts for innovation. Factory managers observed with cautious optimism as machinists and engineers improvised methods to accelerate production. Decisions made in these quiet offices would ripple through assembly lines, ensuring that American aircraft, tanks, and ships could eventually reach front lines fully operational. In essence, the human angle of the bearing crisis revealed a new form of heroism. The courage to innovate under pressure, the discipline to measure and adjust, and the perseverance to overcome obstacles that, on paper, should have halted progress entirely. From these engineers and machinists emerged the invisible backbone of America's industrial war effort, setting the tone for what would become an unprecedented mobilization of human and material resources. The missing bearings and delayed components were more than industrial headaches. They directly influenced tactical planning on the battlefield. Commanders in the Army, Navy, and Air Corps quickly realized that the reliability of machines dictated operational flexibility. Tanks, aircraft, and ships could not be deployed on aggressive schedules if critical parts failed unexpectedly. Early 1940 assessments highlighted this vulnerability. Without dependable engines and drivetrains, maneuvers would be constrained, supply lines jeopardized, and offensive initiatives delayed. Military engineers collaborated closely with industrial counterparts to mitigate these risks. For tanks, this meant redesigning gearboxes and suspension systems to accommodate alternative bearings, ensuring mobility even under high stress. Aircraft units adjusted maintenance schedules and flight operations to account for potential component variability, while naval engineers conducted rigorous turbine trials to confirm performance under load. These adaptations were tactical necessities, ensuring that warfighting capability was preserved despite industrial constraints. The impact was immediate. Units became more self-reliant, capable of operating with less than perfect equipment without catastrophic failure. Field manuals were updated with instructions for handling alternative components. Maintenance crews received training to identify early wear signs and implement rapid fixes. In essence, tactical doctrine evolved in response to industrial realities. Commanders learned to synchronize strategy with logistical and mechanical reliability, creating a feedback loop in which production challenges informed battlefield decisions. This intersection of tactics and industry underscored a crucial principle. Warfare was no longer solely about soldiers and guns. It was about the systems supporting them. A tank might carry a crew of 5, but its effectiveness relied on a network of engineers, machinists, and supply chains capable of keeping bearings turning and engines running. The ability to adapt tactically to equipment limitations became an early hallmark of American operational planning, a resilience that would define engagements in the years to come. With these tactical adaptations, the battlefield became not just a test of force, but a reflection of industrial ingenuity and coordination. The bearing shortage of 1940 became an unexpected catalyst for technological innovation. Engineers across the United States were forced to reconsider the very fundamentals of precision manufacturing. Traditional methods, reliant on exact parts and standardized tolerances, could no longer guarantee continuity. Faced with halted production lines and mounting military demands, inventiveness became a requirement rather than an option. One of the most significant breakthroughs was the adaptation of tapered roller bearings as substitutes for unavailable ball bearings. Originally intended for industrial machinery, these rollers were capable of supporting similar loads while accommodating minor variations in shaft alignment. Engineers redesigned housings, adjusted gear spacing, and tested prototypes under extreme operational conditions. Each successful adaptation validated a new principle. Design could bend to production limitations without compromising functionality. Parallel advances occurred in statistical quality control. Factories began sampling production runs, measuring variations in parts, and implementing real-time corrections. Variations that previously would have halted an entire assembly line were now flagged and adjusted proactively. This approach reduced waste, accelerated throughput, and ensured that military specifications could still be met despite material shortages. The technological angle extended beyond bearings. Engine designs were simplified to accept alternative components. Machine tools were recalibrated for precision under varying material conditions. Assembly lines incorporated feedback loops, allowing errors to be corrected before they compounded. In effect, the crisis forced American industry to invent a new methodology: resilient, adaptive, and self-correcting, a blueprint for wartime production that would soon outpace the Axis powers. From small bearings to entire engines, the technological innovations born from crisis laid the groundwork for the United States' industrial dominance, demonstrating that adaptability and ingenuity could rival even the most meticulously planned systems. The bearing crisis demanded not only engineering skill, but exceptional leadership. Factory supervisors, plant managers, and military planners were suddenly tasked with orchestrating an unprecedented level of coordination across industries, regions, and government departments. Decisions made in offices and conference rooms had direct consequences on frontline readiness, elevating the stakes of organizational leadership to near-combat intensity. Leaders established cross-industry committees to monitor production bottlenecks, track shipments, and prioritize critical components. Meetings once routine now became strategic sessions, where engineers and logisticians collaborated to ensure that every millimeter of steel and every batch of bearings reached its destination on time. Communication networks were expanded, with telegrams, telephone calls, and detailed memos bridging hundreds of miles of factories, shipyards, and arsenals. Leadership became a matter of visibility and oversight, balancing the need for rapid decision-making with technical precision. Military commanders played a crucial role as well. The War Department and Navy coordinated with civilian manufacturers, providing guidance on specifications, delivery schedules, and operational priorities. These leaders understood that industrial agility could directly influence tactical and strategic outcomes. Delays in bearings or gears were not abstract issues. They could determine whether a tank battalion was combat-ready, an aircraft squadron could fly, or a naval vessel could deploy. Leadership had to integrate human, technical, and logistical factors into a cohesive operational framework, often improvising solutions under tight time constraints. This period demonstrated that effective leadership in wartime extended far beyond the battlefield. It required foresight, adaptability, and the ability to mobilize diverse resources toward a single objective, ensuring that industry could meet the demands of war. By coordinating complexity with precision, leaders transformed a national shortage of small components into a learning laboratory for large-scale mobilization, a model that would sustain the United States through years of global conflict. Through strategic oversight, decisive planning, and continuous adaptation, leadership became the silent engine powering America's rise from industrial vulnerability to wartime supremacy. From the vantage point of German and Japanese intelligence, the United States appeared slow, fragmented, and unprepared for large-scale war. Reports emphasized missing bearings, delayed components, and the decentralized nature of U.S. factories. Analysts in Berlin and Tokyo assumed that industrial capacity alone could not compensate for these apparent weaknesses. They predicted that even if America entered the conflict, it would take years to field effective equipment, long after the Axis had secured decisive victories in Europe and the Pacific. Yet what the Axis observers failed to see was the hidden adaptability of American industry. Engineers, machinists, and managers were quietly overcoming shortages through innovation, collaboration, and improvisation. Every delayed shipment or missing component became a catalyst for ingenuity. Small machine shops contributed to larger assembly efforts. Alternative materials were tested, and production processes were redesigned to maintain output despite limitations. These adaptations were largely invisible to foreign intelligence, which could not measure the speed of American problem-solving or the capacity for decentralized innovation. The result was a systematic miscalculation. Axis planners continued to assume that delays would accumulate into critical failures, while in reality, American production lines were steadily learning to operate under constraint. The perceived vulnerabilities, the missing bearings, stalled engines, halted gearboxes, were simultaneously shaping tactical, technological, and organizational resilience. This disconnect between expectation and reality would have profound consequences in the coming years, as the United States entered the war with a level of industrial preparedness that few had anticipated. From the Axis perspective, America's limitations seemed insurmountable. In practice, those same challenges became the crucible that forged industrial ingenuity, turning a potential weakness into one of the most decisive strengths of the Allied war effort. The bearing shortage and the subsequent industrial adaptations carried profound moral and strategic lessons. At its core, the crisis demonstrated that preparedness is not solely about existing resources or pre-war production capacity. It is about the ability to innovate, adapt, and mobilize human talent under pressure. The engineers, machinists, and planners who confronted these shortages exemplified a form of moral resilience. The quiet determination to overcome obstacles, not through heroic gestures, but through meticulous problem-solving and relentless discipline. Strategically, the lesson was clear. Nations cannot rely solely on assumptions about industrial superiority or the apparent strength of their enemies. The Axis powers underestimated the United States, judging it by peacetime metrics and overlooking the latent capacity for rapid adaptation. America's response revealed a new paradigm in modern warfare. Victory would increasingly depend on the speed and efficiency of industrial systems as much as on battlefield tactics or soldier skill. Every innovation, every re-engineered component, and every collaborative effort was a strategic action, shaping outcomes long before the first shots were fired. This moral and strategic dimension extended beyond bearings or production lines. It highlighted the interplay between human ingenuity, leadership, and logistical foresight. Factories became arenas of innovation, engineers became strategic assets, and even minor technical solutions had cascading effects on national preparedness. The experience also fostered a culture of confidence and resilience, proving that the challenges of war could be anticipated, managed, and often converted into advantages. In this light, the missing bearing was more than a production problem. It was a lesson in foresight, adaptability, and the moral imperative to transform limitations into strategic strength. These lessons would resonate throughout the American war effort, defining both industrial and military success in the years to come. By late 1940, the United States had begun forming informal, yet highly effective industrial networks that spanned multiple states and sectors. Factories in Michigan, Ohio, Indiana, and Pennsylvania were no longer isolated production units. They were nodes in a growing system of interdependent operations. When one plant faced shortages or equipment delays, engineers could quickly reroute production, share blueprints, or dispatch alternative components from partner facilities. This network relied on rapid communication and trust. Telegrams and telephone lines carried critical specifications between machine shops and large assembly plants. Engineers documented modifications meticulously, creating a chain of knowledge that allowed each facility to replicate solutions proven elsewhere. This decentralized collaboration contrasted sharply with European models, where centralized control often slowed adaptation. In the U.S., flexibility became a strategic asset. Ingenuity could propagate as quickly as a telegram, allowing the industrial system to correct itself in real time. The results were transformative. Aircraft engines, tank transmissions, and naval turbines reached unprecedented levels of reliability despite material shortages. Small machine shops that had once produced civilian machinery became vital contributors to the war effort. Workers and engineers understood that their innovations were not isolated experiments, but components of a nationwide effort that could tip the balance of the global conflict. This industrial network demonstrated that collaboration and distributed problem-solving could match, and in some ways surpass, the efficiency of rigid centralized systems. America's ability to leverage interconnected expertise would soon translate into a decisive wartime advantage, proving that the sum of adaptive parts could outpace even the most meticulously organized adversaries. The shortage of critical components, such as bearings, forced American industry to confront one of its most pressing wartime challenges: the efficient use of scarce materials. Steel, aluminum, and copper were in high demand, and any misallocation could ripple across multiple production lines. Engineers, metallurgists, and procurement officers worked together to ensure that every ounce of metal was optimized for maximum performance. One approach involved substituting materials without compromising functionality. Bearings, for example, were sometimes produced from alternative alloys, carefully tested to maintain durability under stress. Scrap metal from civilian production was redirected into military applications. Factories adopted tighter quality control to prevent defects, ensuring that fewer materials were wasted in failed components. Even minor adjustments, reducing tolerances slightly or modifying housing designs, allowed engineers to stretch limited resources without undermining operational effectiveness. These efforts had immediate strategic benefits. By conserving materials and maximizing output, the U.S. could accelerate production schedules while maintaining high standards. Aircraft engines were delivered faster, tanks rolled off assembly lines on time, and naval turbines were completed without compromising reliability. This resource efficiency created a multiplier effect. Every unit of material used effectively translated into more combat-ready equipment, directly influencing the United States' capacity to project power abroad. Economically, the crisis highlighted the principle that scarcity could drive innovation. By forcing engineers and managers to rethink materials, production, and design, the United States not only overcame immediate shortages but developed practices that would sustain its industrial dominance throughout the war. What began as a limitation became a strategic tool, demonstrating that intelligent resource management could shape the trajectory of global conflict. Beyond technical and logistical challenges, the bearing shortage tested the morale and psychological resilience of the workforce. Engineers, machinists, and assembly line workers were acutely aware that their efforts had implications far beyond their factories. Each delayed shipment or defective component carried the weight of national defense, and the pressure to innovate quickly was immense. Yet rather than succumbing to frustration, many embraced the challenge, finding pride and purpose in their ability to solve complex problems under duress. Managers fostered this mindset by emphasizing collaboration and recognition. Teams that successfully adapted components or accelerated production schedules were lauded internally, building a culture of innovation and shared responsibility. Engineers kept meticulous notes on experimental solutions, and workshops became hubs of learning where experience was openly shared. This environment reinforced a collective sense of agency. The workforce understood that their ingenuity was directly contributing to the nation's readiness and, ultimately, its survival. Psychological resilience extended to problem-solving under uncertainty. Workers learned to anticipate potential failures, implement preventive measures, and adapt designs in real time. Even when prototypes failed or components broke, these setbacks were framed as necessary steps in an iterative process rather than irreversible mistakes. This mindset not only increased productivity, but cultivated confidence across the workforce, reinforcing the belief that challenges, no matter how daunting, could be overcome with skill, discipline, and ingenuity. The psychological dimension of the industrial response revealed that victory in modern warfare depended not only on machines or materials, but on the human capacity to innovate, adapt, and persevere. Confidence and morale within factories became a quiet yet decisive force, ensuring that America's industrial engine could overcome obstacles that, to external observers, seemed insurmountable. The bearing shortage and the resulting industrial innovations provided early strategic lessons that would shape America's approach to global warfare. Military planners and industrial leaders recognized that success in modern conflict required more than tactical brilliance on the battlefield. It required the ability to mobilize, adapt, and sustain production at a national scale. The crisis underscored the vital link between industrial capacity and military readiness, highlighting that delays in the factory could translate directly into vulnerabilities on the front lines. These lessons prompted a reevaluation of strategy. Commanders began coordinating closely with industrial engineers to ensure that planned operations could be supported by available equipment. Contingency plans accounted not just for enemy actions, but also for potential mechanical failures, delayed deliveries, and resource shortages. In effect, strategic planning extended from the battlefield to the assembly line, integrating production realities into military decision-making. The experience also revealed the importance of adaptability. American industry learned to function under constraints, improvising solutions and redesigning components without halting production. This approach would prove decisive once the United States entered the war in full, allowing rapid escalation of output across aircraft, armored vehicles, and naval vessels. By turning potential weaknesses into opportunities for innovation, the nation demonstrated that industrial agility could serve as a strategic force multiplier. Axis powers, observing from afar, remained largely unaware of these transformations. Their misperception that America's industrial system was slow, rigid, and ill-prepared would lead to critical underestimations in the early years of conflict. Meanwhile, U.S. planners quietly solidified the foundations of a wartime economy capable of overwhelming the Axis through sheer scale, efficiency, and adaptability. The bearing shortage of 1940, once a minor technical problem, thus became a profound strategic lesson. Preparedness, ingenuity, and coordinated industrial effort were as decisive as any battle, laying the groundwork for America's eventual global dominance in World War II. Following the industrial breakthroughs of early 1941, American military planners began translating production gains into operational readiness. Field exercises across the continental United States tested newly produced aircraft, tanks, and naval vessels under conditions that closely simulated wartime deployment. These exercises marked the first opportunity to observe whether the innovations born from bearing shortages could withstand real operational stress. At Wright Field in Ohio, Army Air Corps units conducted intensive flight trials of aircraft equipped with Pratt & Whitney, R. 1830 engines fitted with tapered roller bearings. Planes were flown at maximum speed and altitude for extended periods, performing maneuvers that pushed engines to their limits. Reports confirmed that the modifications had eliminated previous failures. Squadrons trained with renewed confidence, knowing their engines could endure prolonged missions without breakdowns. Maintenance crews were also trained to handle these new tolerances, further reducing the risk of operational delays. The success of these exercises validated the industrial solutions and reinforced the tactical doctrine that equipment limitations no longer dictated operational planning. Armored units at Fort Knox and Camp Beauregard underwent similar evaluations. M2 and early M3 tanks traversed rugged terrain, engaged in mock battles, and operated in continuous maneuvers over multiple days. The redesigned drivetrains and alternative bearings ensured reliability even under extreme conditions. Tank crews reported smoother handling, fewer mechanical failures, and increased endurance compared to previous models. Commanders used these results to update operational tactics, permitting more aggressive maneuvers, faster advances, and reduced logistical dependencies. The integration of industrial innovation directly influenced tactical planning, proving that production adaptability could shape battlefield strategy. Naval deployments also reflected these advances. Newly completed destroyers and cruisers were subjected to extended sea trials along the Atlantic coast and the Gulf of Mexico. Turbines with alternative bearings operated continuously for days, maintaining speed and maneuverability without overheating. Naval engineers and crews noted a significant reduction in component failures, enabling commanders to plan longer patrols and more complex exercises with confidence. These trials demonstrated that the industrial problem-solving of the past year had tangible, operational consequences, directly enhancing U.S. naval readiness. Meanwhile, Axis intelligence continued to miscalculate American capabilities. Reports of increased aircraft output and improved reliability of armored vehicles and naval vessels contradicted earlier assumptions, but lacked sufficient detail for German and Japanese planners to appreciate the full extent of the industrial transformation. The perception gap allowed the United States to continue refining its production and deployment strategies without alerting adversaries to the magnitude of its growing advantage. The convergence of industrial, technological, and operational breakthroughs culminated in a profound strategic inflection point. By mid-1941, American forces could train, equip, and deploy units with equipment previously deemed vulnerable due to component shortages. The success of field exercises and sea trials validated months of innovation, demonstrating that adaptive problem-solving could overcome systemic production limitations. This turning point not only addressed immediate tactical concerns, but also established a blueprint for scaling production and deployment as the nation moved closer to direct engagement in the global conflict. The decisive moment of early 1941, therefore, was not defined by a battlefield victory, but by the seamless integration of industrial innovation into operational capability. It marked the point where American ingenuity had transformed a logistical vulnerability into a strategic asset, laying the foundation for the country's eventual supremacy in both production and combat. With industrial adaptation fully validated by early 1941, the United States began the careful process of transitioning from preparation to deployment. Though the nation had not yet formally entered World War II, exercises and mobilizations mirrored operational realities, allowing both Army and Navy units to test new equipment in simulated combat scenarios. These deployments revealed how industrial solutions directly influence strategic planning and force readiness. In the skies, Army Air Corps squadrons equipped with aircraft powered by engines fitted with redesigned bearings undertook extended reconnaissance and mock combat missions. Pilots reported unprecedented engine stability and endurance, enabling longer patrols and sustained maneuvers that previously risked mechanical failure. Training exercises simulated rapid response to enemy attacks, integrating lessons learned from European theaters where operational tempo demanded reliability. The success of these missions underscored the direct link between factory ingenuity and battlefield effectiveness. Armored units likewise demonstrated remarkable performance. M3 tanks, previously prone to drivetrain issues, now completed multi-day maneuvers across rugged terrain without mechanical stoppages. Armored brigades practiced coordinated assaults, relying on the reliability of each vehicle to maintain formation and momentum. The redesign of gearboxes and the integration of alternative bearings allowed commanders to implement more aggressive strategies and exercises, confident that equipment would not hinder operational execution. Tactical doctrine evolved in real time, blending mechanical reliability with strategic flexibility. Naval forces took similar steps. Newly commissioned destroyers and light cruisers conducted multi-day sea trials along the Atlantic seaboard, simulating convoy escort missions and fleet maneuvers. Turbines with tapered roller bearings performed flawlessly under extended operation, allowing ships to sustain high speeds without overheating or component failure. Naval commanders used these exercises to refine deployment schedules, optimize maintenance protocols, and develop coordinated fleet operations, an essential prelude to eventual global deployment. Axis observers remained largely unaware of the significance of these developments. German and Japanese intelligence continued to assume that industrial bottlenecks would delay American readiness. Reports of incremental production improvements failed to convey the systemic adaptability and operational integration now in place. The miscalculation would later have profound consequences, as the United States would enter the war with not only material superiority, but a tested, reliable, and flexible industrial and operational framework. By mid-1941, the decisive turning point had been reached. American forces could now operate with confidence, using equipment previously considered unreliable, and the foundation was laid for rapid escalation once the nation formally entered the conflict. Industrial innovation had seamlessly translated into tactical and strategic advantage, setting the stage for the first tangible demonstrations of U.S. operational supremacy. As 1941 progressed, the United States moved closer to full-scale mobilization, and the benefits of industrial adaptation became increasingly visible. Training exercises evolved into near-realistic operational deployments, preparing units for eventual combat. Army, Navy, and Air Corps planners used these exercises to identify and resolve remaining weaknesses, while field data validated the efficacy of previously experimental engineering solutions. In armored warfare simulations, combined tank and infantry units conducted large-scale maneuvers across the Midwest. M3 tanks, with reinforced drivetrains and adapted bearings, operated continuously for over a week without significant mechanical issues. Engineers accompanied these units in the field, monitoring performance, recording data, and implementing rapid fixes for minor wear and tear. Commanders observed that vehicles could sustain continuous operations, allowing coordinated movements over challenging terrain, an essential precursor to deployment in Europe and North Africa. Tactical doctrine incorporated these observations, emphasizing speed, coordination, and flexibility rather than cautious, incremental advances. The Air Corps mirrored these advancements in simulated combat zones. Squadrons undertook long-range reconnaissance missions and mock bombing runs using aircraft powered by engines retrofitted with tapered roller bearings. Reliability and endurance improved markedly, reducing risk for pilots and increasing training efficiency. Maintenance protocols evolved to anticipate minor component variability, ensuring that aircraft could be returned to service quickly. This integration of production adaptation into operational practice gave the Air Corps an unprecedented level of readiness, bridging the gap between factory innovation and tactical execution. Naval forces conducted extended fleet exercises, simulating convoy protection and coordinated offensive maneuvers in the Atlantic. Turbine engines performed without overheating, and ships maintained high-speed formations over long durations. Engineers tracked performance data in real time, refining operational procedures and ensuring that mechanical reliability translated into actionable strategic advantage. These exercises demonstrated that the industrial solutions implemented over the previous year could withstand sustained, realistic operational demands. From the Axis perspective, early 1941 remained a period of misjudgment. German and Japanese intelligence observed increases in American production and field exercises, but failed to recognize the systemic adaptability that underpinned these improvements. They continued to assume that delays, bottlenecks, and component shortages would compromise readiness, a critical underestimation that would have strategic consequences once the United States entered the war. The culmination of early 1941's deployments marked a decisive turning point. American forces were not only equipped but operationally tested, validated, and ready for large-scale engagement. The successful integration of industrial innovation, field training, and tactical adaptation ensured that the United States would enter the global conflict with both material superiority and the operational confidence necessary to leverage it effectively. By mid-1941, the immediate consequences of America's industrial adaptations began to manifest across multiple fronts of preparation, signaling a profound shift in the nation's readiness for global conflict. Factories that had once struggled with missing bearings now operated at sustained capacity, producing aircraft, tanks, and naval vessels with unprecedented consistency. Production metrics reflected the success. Output of the Pratt Whitney R-1830 engines surged, M3 tank assemblies doubled in reliability, and naval turbines completed on schedule allowed shipyards to accelerate commissioning. The impact on military planning was immediate. Commanders, previously constrained by equipment uncertainty, now had greater latitude in training exercises and strategic simulations. Armored divisions could plan multi-day maneuvers without interruption. Air Corps squadrons could conduct extended sorties with fewer mechanical setbacks, and naval forces could simulate long-distance patrols without the risk of engine failure. The operational tempo increased, building confidence across all branches and providing a critical rehearsal for eventual deployment overseas. This newfound industrial consistency also reinforced the psychological resilience of the workforce and command structures. Engineers, machinists, and military planners observed tangible results of their problem-solving efforts. The morale boost was palpable. What had once been a source of frustration, the missing bearings, had become evidence of the nation's capacity to overcome adversity through innovation and coordination. Military leaders could now trust that logistical and mechanical constraints would not hinder operational planning. allowing strategic decisions to focus on enemy movements and battlefield tactics rather than production limitations. From a broader perspective, the aftermath of these industrial innovations revealed early signs of American strategic advantage. Axis intelligence continued to underestimate the speed and effectiveness of U.S. production, unaware of the systemic improvements across factories, supply chains, and field integration. This miscalculation would have profound implications once America entered the war formally. The disparity between perceived vulnerability and actual capability created a buffer that allowed the U.S. to refine production processes, train personnel, and validate equipment under realistic conditions, preparing the nation to enter the conflict with both material superiority and operational confidence. In essence, the aftermath of early industrial adaptation demonstrated that logistical challenges, when addressed through ingenuity, coordination, and perseverance, could transform potential weaknesses into strategic assets. The nation had not only solved a technical problem, but had also established a model for large-scale mobilization, ensuring that the machinery of war, both human and mechanical, was ready to respond effectively to the challenges of global conflict. As the nation stood on the precipice of full-scale engagement, the lessons of the Bering Crisis had solidified. Preparation, innovation, and adaptability were as decisive as the weapons themselves, setting the stage for the United States to project power efficiently and decisively in the years ahead. By late 1941, the cumulative effects of America's industrial adaptations were becoming increasingly visible on both strategic and operational levels. Factories operated at full capacity, producing essential equipment at rates previously deemed impossible under the constraints of 1940. The production of M3 tanks, aircraft engines, and naval turbines not only reached planned targets, but exceeded them, reflecting the successful integration of alternative components, redesigned systems, and coordinated industrial networks. The scale-up had immediate operational consequences. Army training exercises across Fort Knox, Camp Beauregard, and other armored centers demonstrated that tanks could perform extended maneuvers without mechanical failures. Brigades now had the confidence to practice combined arms operations, integrating infantry and artillery with armored units in complex tactical exercises. Similarly, the Air Corps expanded its training programs, leveraging the reliability of retrofitted engines to conduct long-range reconnaissance, simulated bombing runs, and intensive aerial maneuvers. These exercises not only tested equipment, but also trained personnel in operational procedures reflective of imminent combat scenarios. Naval forces benefited equally from the scale-up. Newly commissioned destroyers and cruisers, equipped with turbines using alternative bearings, demonstrated operational readiness during extended sea trials. Fleet exercises simulated convoy escort missions and coordinated fleet maneuvers, refining tactics and ensuring that crews could maintain speed and formation over extended periods. The reliability of engines allowed naval planners to schedule more complex operations with confidence, reducing the risk of delays or mechanical failures during actual deployment. Economically, the aftermath of the Bering Crisis also highlighted the efficiency of American resource management. By optimizing material usage, implementing alternative alloys, and minimizing waste, factories sustained high output without overtaxing limited resources. This efficiency reinforced confidence in the nation's ability to sustain prolonged production, ensuring that equipment supply would match the pace of expanding operational demands. From the Axis perspective, these developments remained largely underestimated. German and Japanese intelligence continued to perceive American industry as sluggish and fragmented, failing to recognize the systemic innovations that allowed for rapid scaling and operational integration. This misperception would become a critical advantage, providing the United States with a strategic buffer during the early phases of its eventual wartime engagement. By the end of 1941, the industrial crisis that began with a simple shortage of ball bearings had been fully transformed into a foundation for operational and strategic advantage. America's production networks, adaptive workforce, and coordinated planning had created a robust system capable of sustaining high-intensity operations, ensuring that the nation was prepared to enter the global conflict with both material and operational superiority. By early 1941, the cumulative efforts of engineers, factory managers, and military planners reached a critical inflection point. The bearing shortages that had constrained production for over a year were now being systematically resolved through innovation, adaptation, and coordination. Factories across the Midwest and Northeast had fully implemented alternative designs for aircraft engines, tank drivetrains, and naval turbines, allowing production lines to operate at unprecedented rates. These technical achievements were not abstract victories. They had immediate operational consequences, directly affecting readiness for future combat engagements. One of the most significant turning points occurred in Detroit and Dayton, where aircraft engine production had been consistently delayed due to unavailable ball bearings. By January 1941, engineers had successfully integrated tapered roller bearings into the Pratt Whitney R-1830 twin Wasp engine, the primary power plant for both Army Air Corps and Navy aircraft. Field testing demonstrated that the modified engines could sustain prolonged high-speed operation without failure, a critical milestone that validated both the technical approach and the broader methodology of adaptive engineering. The success reverberated through other production centers, providing a replicable template for addressing similar shortages in tank transmissions and naval turbines. Simultaneously, tank manufacturing in Indiana and Ohio reached a decisive phase. The M2 and early M3 series tanks, which had previously suffered from gearbox failures due to bearing limitations, now incorporated redesigned drivetrains with reinforced housings and recalibrated tolerances. Test regiments at Fort Knox reported a dramatic increase in operational reliability. Tanks could traverse rough terrain, sustain extended maneuvers, and maintain combat readiness over multiple days of field exercises, achievements that had been impossible during the peak of component shortages. Military commanders quickly updated tactical manuals to reflect this newfound reliability, allowing armored units to plan more aggressive maneuvers and reduce reliance on cautious, incremental advances. Naval programs mirrored these advances. In Philadelphia, Norfolk, and along the Gulf Coast, shipyards implementing alternative bearings for turbines saw a marked improvement in construction schedules and propulsion reliability. By February 1941, destroyers undergoing sea trials demonstrated that their engines could operate continuously for extended periods without overheating or component failure. These results allowed naval planners to confidently schedule deployments, knowing that newly commissioned vessels could meet operational expectations. The psychological impact of these successes was equally profound. Engineers, machinists, and military officers witnessed the tangible results of their labor. Delayed engines were now functional, tanks were fully operational, and ships were ready for deployment. Confidence surged across the industrial workforce and command structures, reinforcing the belief that American ingenuity could overcome constraints previously deemed insurmountable. For the first time, the United States had transformed a chronic industrial vulnerability into a foundation for strategic advantage. From an enemy perspective, the implications were immediate and unsettling. Axis intelligence reports still assumed that American production would falter under pressure. Yet by early 1941, evidence suggested otherwise. German and Japanese analysts began noting increases in American aircraft production rates and improvements in armored vehicle reliability, although the full scope of adaptive innovation remained largely invisible. This discrepancy between perception and reality would later become a decisive factor, as Axis planners continued to underestimate the speed and effectiveness of U.S. industrial mobilization. The convergence of these industrial breakthroughs set the stage for broader operational planning. Military leaders now had the confidence to integrate new aircraft, tanks, and naval vessels into forward deployment exercises, preparing both personnel and command structures for eventual large-scale engagement. The once overwhelming limitations imposed by missing bearings were no longer obstacles. They had catalyzed a nationwide network of innovation, problem-solving, and resilience that would define American readiness in the months leading up to direct participation in World War II. In essence, the turning point of early 1941 was not a single battle or campaign, but a nationwide achievement in industrial adaptation, where ingenuity, collaboration, and leadership combined to turn a logistical vulnerability into a decisive strategic advantage, setting the United States on a trajectory toward wartime supremacy. As 1942 approached, the broader consequences of America's industrial adaptations became increasingly evident, not only in production figures, but in strategic planning and international perception. The ability to solve the bearing shortage and sustain high-output manufacturing sent ripples through every branch of the U.S. military, reinforcing confidence in both equipment and operational strategy. Commanders now planned for large-scale deployments with the assurance that tanks, aircraft, and ships would function reliably, enabling more ambitious training exercises and coordinated maneuvers across multiple theaters. The Army's armored divisions were particularly transformed, with redesigned M3 tanks performing consistently under extended field conditions. Brigades expanded the scope of their exercises, integrating live-fire drills, cross-terrain maneuvers, and combined operations with artillery and infantry units. Officers reported a significant reduction in mechanical failures, which allowed exercises to closely simulate the stresses and uncertainties of actual combat. This operational readiness created a feedback loop. Soldiers trained on reliable equipment developed greater confidence and tactical sophistication, which in turn improved the effectiveness of simulated engagements and future battlefield performance. The Air Corps leveraged similar advantages. Long-range bombing exercises, reconnaissance flights, and simulated interception missions all benefited from reliable engines and improved maintenance protocols. Squadrons trained at higher tempo and over greater distances, creating a pool of pilots and crews familiar with operational demands that would soon define overseas engagements. The reliability of machinery allowed leadership to focus on tactical execution and coordination rather than contingency planning for mechanical failures, elevating overall combat readiness. Naval forces experienced parallel improvements. The successful integration of alternative bearings and turbines enabled longer, more complex fleet operations. Exercises simulating convoy escort, anti-submarine patrols, and coordinated amphibious support operations demonstrated the capacity of vessels to sustain prolonged high-speed operation. Commanders could now test full fleet formations and refine tactical doctrines with confidence that mechanical reliability would not impede operational planning. From a strategic standpoint, these adaptations fundamentally shifted America's approach to the global conflict. Leaders recognized that industrial problem-solving could be as decisive as battlefield victories. The United States had effectively converted a logistical weakness into a strategic advantage, demonstrating that adaptability, innovation, and coordinated planning were integral to sustained military dominance. The aftermath of industrial adaptation was thus a dual phenomenon. It strengthened operational readiness while reshaping strategic thinking, providing the United States with both material superiority and the confidence to project power on a global scale. By mid-1942, the full impact of America's industrial adaptations was measurable not only in operational readiness, but in tangible metrics of production, efficiency, and battlefield preparedness. Tank production had increased dramatically, with M3 and M4 models rolling off assembly lines at rates that exceeded pre-war projections. Aircraft engines, now standardized with alternative bearing solutions, were being produced and deployed at an unprecedented pace, ensuring that both Army and Navy aviation units were equipped with reliable, combat-ready planes. Naval vessels, including destroyers and cruisers, benefited from turbines capable of sustained operation, allowing fleets to conduct extensive operations without the risk of mechanical failure. The quantitative improvements reinforced qualitative advantages. Units trained and equipped with reliable machinery were far more capable of executing complex maneuvers, whether in armored divisions, aerial squadrons, or naval fleets. Field exercises reflected this readiness, demonstrating that American forces could maintain operational tempo over extended periods, an advantage previously unattainable during the bearing shortage crisis. Commanders could now plan larger-scale operations with confidence, knowing that equipment would support strategic objectives rather than constrain them. The Axis powers slowly began to recognize the implications of these developments. Intelligence reports from Berlin and Tokyo noted increases in American production, improvements in equipment reliability, and the apparent operational readiness of newly deployed units. While analysts initially underestimated the systemic efficiency behind these gains, the cumulative effect was undeniable. America was rapidly transforming from a nation perceived as industrially constrained into a fully mobilized, resilient, and adaptive wartime power. These shifts also influenced strategic planning. Allied commanders integrated industrial lessons into broader operational doctrine, emphasizing the importance of logistics, maintenance, and production capacity in achieving long-term battlefield success. The ability to rapidly replace or repair equipment became as critical as the weapon systems themselves, shaping tactical decisions and ensuring that units remained combat effective even under sustained engagement. The aftermath of America's industrial innovation was a decisive reinforcement of operational and strategic strength. From production numbers to field readiness, the crisis had evolved into a framework of efficiency, adaptability, and foresight, giving the United States an unparalleled advantage in both material resources and combat preparedness. By the summer of 1942, the nation stood ready to leverage these gains, with the Axis powers increasingly aware that the American industrial engine had transformed potential weakness into strategic dominance. The bearing shortage of 1940, initially a minor technical problem, evolved into a defining moment for American industry, military planning, and strategic foresight. What began as a vulnerability, missing components that threatened to halt critical production, became a crucible for innovation, coordination, and resilience. Engineers, machinists, planners, and commanders transformed constraint into opportunity, demonstrating that human ingenuity, when combined with disciplined organization, could overcome even systemic logistical challenges. This episode revealed a broader truth about modern warfare. Industrial capacity and adaptability are as decisive as battlefield tactics. The ability to produce reliable tanks, aircraft, and naval vessels at scale ensured that the United States could project power globally, sustain long-term operations, and respond rapidly to unforeseen challenges. Equally important, the crisis fostered a culture of innovation and collaboration, embedding lessons in problem-solving and coordination that would carry the nation through years of intense conflict. From a historical perspective, the events surrounding the bearing shortage underscore the interconnectedness of technology, strategy, and human effort. Every recalibrated gearbox, every alternative bearing, and every re-engineered engine was a microcosm of larger strategic success. The American workforce became an unseen frontline, where perseverance, skill, and adaptability shaped outcomes that would ripple across theaters of war. In contrast, Axis powers, despite their early confidence, remained unaware of the systemic transformations taking place, leading to miscalculations that would influence the course of the conflict. Ultimately, the crisis demonstrates that true strength in wartime extends beyond weaponry and numerical superiority. It resides in the capacity to adapt, to learn from scarcity, and to turn limitations into advantages. The United States' response to the missing ball bearings exemplifies this principle, showing how a nation's ingenuity and industrial might can reshape not only its own fate, but the trajectory of global events. In the end, the bearing shortage was more than a technical challenge. It was a proving ground for American innovation, resilience, and strategic foresight, laying the foundation for industrial dominance, military effectiveness, and historical legacy.